All right, get this. We're about to jump headfirst into this wild connection that'll probably have you wondering how we even got here.
I'm excited.
You know how we were digging into Stefan Banach and neural networks?
Yeah.
Well, buckle up, because the link is way more mind-blowing than you might think. We're talking about a trail of breadcrumbs, but instead of leading to, like, a hidden room, it goes from a Polish cafe straight to the cutting edge of AI.
Seriously, it's crazy how Stefan Banach's work, which seemed, I don't know, kind of out there at the time, is actually crucial for understanding how AI learns.
No kidding. I mean, think about it. We're talking about the universal approximation theorem, this idea that a neural network, if you make it big enough, can basically learn to predict anything.
Right. It's wild.
But here's the kicker. Banach's work, way back in the early 1900s, plays a huge role in all of this. So let's back up a bit for a second.
Uh-huh.
Who is this Stefan Banach guy?
Well, picture this Krakow, 1892. That's where Banach enters the scene. He's considered a co-founder of this thing called functional analysis.
Okay,
Now, I know that sounds kind of intimidating,
it's just a tad.
but stay with me for a second. Imagine you're looking at a star chart, right? You're not just focused on one single star. Functional analysis is kind of like that, but instead of stars, we're talking about functions as points in a much bigger space.
Okay, so instead of getting lost in the weeds of one equation, he was searching for those big picture patterns and connections between functions themselves.
Exactly. And get this, his insights ended up giving future mathematicians and computer scientists, the folks working on AI and all that, some really essential tools, even if they didn't even realize it at the time.
Wow. So he's basically laying the foundation for a building that no one even knew would exist yet.
Exactly. What's even cooler is that Banach didn't exactly take the straight and narrow path to becoming a math legend.
Really? What do you mean?
At first, he was studying engineering, believe it or not.
No way.
Yeah. It wasn't until he bumped into another mathematician, Hugo Steinhaus, talk about a life-changing encounter. Suddenly, he was hooked on pure math.
It's like something out of a movie, like a chance meeting that changes the course of scientific history.
Didn't he end up doing a lot of his work in cafes, too?
He did. The cafes in Olwell were like his research lab. It just shows you that breakthroughs can happen anywhere. Sometimes you just need the right mix of, caffeine and inspiration.
I love that. Okay, so Banach lays down this groundwork for functional analysis, but how on earth does that connect to neural networks, which are like everywhere in AI today? It's like we're connecting a puzzle piece from a century ago to the tech that's shaping the world right now.
I know, right? It's mind-blowing. And the connection really comes alive when we look at a couple of Banach's biggest contributions, the Hahn-Banach theorem and the Ries representation theorem. They were like essential clues that helped us understand how neural networks learn.
Okay, I think we need to break that down. First up, for everyone listening who might not be, math whizzes, what exactly is the universal approximation theorem? Imagine this. You could teach a computer to predict anything that changes smoothly over time, like stock prices, the weather, even how traffic moves through a city, you name it. The universal approximation theorem basically says that if you have a big enough neural network, you can train it to do just that.
That's seriously cool, but how does it actually work? Like when you really break it down, neural networks seem kind of straightforward. They're just layers of these interconnected nodes doing calculations.
And the way we talk about them now is usually feed forward, meaning the information flows in one direction. You've got an input layer, that's where the info comes in. Then it goes through one or more of these hidden layers. And finally, it reaches the output layer, which gives you the result.
It's like a relay race. Each runner passes the baton to the next.
Exactly. And here's the thing. The real magic is in the connections between those runners. We call those the weights.
Weights.
Yeah. These weights, they decide how much influence each input has on the final output. So by adjusting those weights, the network learns how to approximate different functions and make predictions.
So if we can just figure out the right way to adjust these weights, we can essentially teach a neural network to mimic any process we can describe with math.
That's the idea, yeah. That's the power of the universal approximation theorem in a nutshell. Now, of course, there are some pretty big ifs involved. Like, the theorem doesn't tell us how big the network needs to be for a specific problem. It also doesn't say how to find those perfect weights.
And that's the real challenge, right? It's like having a treasure map, but it only tells you the treasure is out there. It doesn't give you the X that marks the spot.
Exactly. And that's what keeps AI researchers busy figuring out those details. The network size, the weights, that's the real quest. But the universal approximation theorem, it's like their compass, It reassures them that they're not on a wild goose chase. The potential's definitely there.
Right, like there's a light at the end of the tunnel, even if it's still pretty far off. But okay, so we've got this awesome potential because of the universal approximation theorem.
Yeah.
But I feel like we skipped a step. We started with Banach in that cafe, coming up with these really out there mathematical ideas, and now we're talking about super advanced AI. How do we get from point A to point B?
That's where things come full circle, believe it or not. Remember those theorems we talked about earlier, the Hahn-Banach theorem and the Rees representation theorem? They're not just some abstract math problems. They actually have a huge impact on how we understand and build AI today.
All right, lay it on me. What's the connection?
Let's start with the Hahn-Banach theorem. Now, bear with me here, because this is where it gets kind of cool. Think about a neuron in your brain, right? Imagine it's like a picky eater.
A picky eater. Okay, now you've got my attention.
So each neuron gets all this information. Those are its inputs. But it only really cares about certain combos of those inputs, specific things. It's like that neuron saying, I only want to deal with this much of this input and a whole lot of that one, but none of that other stuff. So the Hahn-Banach theorem basically says that we can make sure each neuron is like looking at the right combo of inputs to learn the right stuff.
Interesting. So even though Banach was doing his thing decades before AI even existed, he kind of stumbled on a key principle behind how AI learns today.
It's wild.
Totally. What about the Rees representation theorem? Where does that fit into all of this?
Okay, so the Rees representation theorem, that one's really cool because it gets to the heart of how neural networks are actually structured. It basically gives us this way to represent linear functionals, remember those picky eater neurons, as these things called inner products.
Inner products. That rings a bell, but I think I need a refresher. What are those again?
Right, so imagine you meet someone new and you're trying to find things you have in common, right? The more you have in common, the higher your, similarity score. Inner products are kind of like that, but for vectors, which are just lists of numbers. And here's the mind-blowing part. Neurons in a neural network, they use something like inner products too.
Get out. So the way our brains figure things out might actually mirror this abstract mathematical concept.
Yeah, it's pretty neat. So every neuron in a neural network takes a weighted sum of its inputs, and that's essentially an inner product. It's like each neuron is checking how similar the incoming info is to its own set of weights.
That's incredible. It's like Banach left instructions for building artificial brains a century before anyone even thought of it.
This makes me think about those early neural networks, though, the perceptrons. Weren't those kind of limited in what they could do?
Yeah, you're right. Perceptrons, they're like the Model T of neural networks. They were great for certain tasks, but they had one major flaw. They could only learn what we call linearly separable functions. Okay, hold up linearly separable functions. Could you maybe explain that a little?
Sure. Picture this. You've got a bunch of marbles, some blue, some red, scattered on a table. If you can draw one straight line to perfectly separate the blue marbles from the red marbles, that's a linearly separable problem. And perceptrons, they ace those kinds of problems.
Okay, I get it. So what happens when you can't separate the marbles so easily? Like, what if they're all mixed up?
See, that's where perceptrons hit a wall. They just couldn't deal with problems that weren't linearly separable. And there's this classic example that shows this perfectly. The XOR function.
XOR. That sounds familiar, but I can't quite place it.
No worries. The XOR function stands for exclusive OR. It's like a little logic puzzle. Imagine two light switches. The XOR function only gives you true, or let's say the light turns on if exactly one switch is flipped on. If both are off or both are on, the light stays off.
Oh, right. I remember that now. So how does that mess with our perceptron?
Well, if you try to picture that XOR function with our marble example, you can't draw just one straight line to separate the light on cases from the light off cases. It's impossible. And that, my friend, is the big limitation of a single perceptron.
So the XOR function, it's like kryptonite for a perceptron. But that's where the whole universal part of the universal approximation theorem comes in, right?
What about it? To unlock the true power of neural networks, to get that universal approximation, we have to go beyond the simple perceptron. We got to add more layers, and that's where hidden layers come into play.
Hidden layers. So you're saying if we just add more layers to our neural network, if we make it deeper, we can get past the limitations of those old school perceptrons.
Exactly. Even adding just one hidden layer, which creates what we call a shallow neural network, makes a world of difference. It's like giving our network a serious upgrade.
An upgrade, huh? That sounds promising. What's so special about this hidden layer?
That single hidden layer, it lets the network create way more complex decision boundaries. Remember how the perceptron struggled to separate those marbles if they weren't all lined up? Well, a hidden layer, it's like giving the network the ability to draw curves, loops, all these intricate patterns so it can separate those marbles perfectly, even if they're all jumbled up.
So even a shallow neural network, just one hidden layer, can handle something like that XOR function
Yeah.
that totally stumped a single perceptron.
You got it. That extra layer allows it to learn the XOR function without breaking a sweat. In fact, with the right setup of neurons and weights in those hidden layers, it can approximate any continuous function we throw at it. And that's what makes the universal approximation theorem so powerful.
Wow, okay. So adding hidden layers is like giving our neural networks a super brain boost.
Mm.
But how in the world do we know how many neurons to put in those hidden layers? And how do we adjust all those weights to make sure everything works right?
That's the million-dollar question. And honestly, this is where the universal approximation theorem, as cool as it is, kind of leaves us hanging. It tells us a network exists that can do the job, but it doesn't tell us how big it needs to be or what the exact recipe for those weights is. That's a big part of what keeps those AI researchers up at night.
I can only imagine. It's like having a key that can unlock any door in the world, but you've got to find it in a haystack of millions of other keys. Exciting, but also a little intimidating.
You said it. And it gets even trickier when you realize that we often don't even know what the perfect solution looks like in the first place. We're asking these networks to find patterns and make sense of huge amounts of data that even we might not fully understand.
It's like sending an explorer to a new planet with a map that only tells them the planet exists, but doesn't show them how to get there.
Exactly. And that's what makes AI research so fascinating. We're pushing the boundaries of what's possible, and we're learning as we go.
So we've got these neural networks, these incredibly intricate systems with all these interconnected parts, and we're basically asking them to learn from all this data, right? To find those hidden patterns and make sense of the world. But how do we ensure they're actually learning the right things, especially when we're training them with, like, a limited amount of data?
That, my friend, is where Banach's work comes in clutch once again.
It's like we're showing them a tiny piece of a giant puzzle and hoping they can figure out what the whole picture looks like.
Exactly. And that's where, believe it or not, the Hahn-Banach theorem comes in to save the day. Remember how it basically says we can extend those linear functionals, those picky eater neurons. We can make sure those picky eaters are looking at the right things without messing up how they work.
Right, like making sure each neuron is paying attention to the right clues, so to speak.
And that ability to extend those calculations to go beyond the specific examples the network has seen, that's what lets those networks actually generalize.
Generalize.
Yeah. It means they can take what they've learned from that small sample of data and actually apply it to new, unseen situations.
So it's like, I don't know, learning to ride a bike. You start with training wheels, maybe a few wobbly trips down the sidewalk.
Right.
But eventually you want to be able to ride on different surfaces, go up hills, dodge obstacles.
Exactly. And in a way, the Hahn-Banach theorem gives us like a theoretical guarantee that our neural networks can do that too. It tells us those calculations happening inside, those connections between neurons, they can handle more than just what they've been explicitly trained on.
It's like Banach gave us this mathematical safety net to make sure our AI systems don't just become parrots, repeating what they've heard, but actually learn and adapt.
I like that, a mathematical safety net.
And speaking of Banach's genius, what about the Rees representation theorem? We talked about how it connects to the actual structure of neural networks. But how does that play out in the real world? How does it affect how these AI systems actually work?
Well, remember how that theorem basically shows that linear functionals are picky eater neurons, again, can be represented as inner products, and how those inner products are like measures of similarity?
Yeah, it's like each neuron was doing a how alike are these things check with its input.
Exactly. Think about how much we rely on similarity in our own lives. When you're recognizing a face, you're comparing it to all the faces you've ever seen, looking for those similarities.
Right.
When you recommend a song to a friend, you're thinking about their taste in music, trying to find something similar to what they already like.
And we do this all the time without even thinking about it.
That's the thing. And the Rees representation theorem, as mind-boggling as it might seem, it gives us a way to understand how those similarity judgments, those comparisons, can be captured and even replicated in AI systems. It's like Banach, without even knowing it, was giving us a glimpse into the fundamental language of intelligence itself.
It's pretty incredible when you think about it like that. We've gone from Stefan Banach hanging out in a cafe 100 years ago coming up with these groundbreaking mathematical ideas, to these powerful AI systems that are changing the world right in front of us.
It just goes to show you never know what amazing connections and breakthroughs are waiting to be discovered when you start exploring those seemingly unrelated fields.
Absolutely. It's like Banach left a trail of mathematical breadcrumbs, and now, all these years later, AI researchers are following that trail to build the future. And for everyone listening, I hope this has inspired you to do a little exploring of your own. You never know what amazing things you might find when you start connecting those dots, those ideas that might seem totally unrelated at first glance. Who knows? Maybe you'll be the one to uncover the next big breakthrough.